In this series, we're writing the microcode for the SAP6502, which is programmed into the EPROMs on the lower left-hand side. The code's available on GitHub, with CPU_v2 being the latest version, and this previous video linked below shows you how to install it. The main idea of this series is take the SAP1, originally designed by Albert Paul Malvino and popularized by Ben Eater, and add a little muscle to the bone. Enough, in fact, to make it 6502 compatible. I'm going to go off on a tangent for a little bit here, but I promise I'll bring it back to the topic at hand. Here we have Arnold Schwarzenegger and Jesse the Body Ventura. They both starred in Predator, a 1987 cult classic. Here's Jesse Ventura.
All painless is waiting.
Arnold Schwarzenegger. And the Predator. This computer-generated, transparent water or glass effect became very popular at the time. Then in 1989, James Cameron's Abyss took it to a whole new level. You only need to compare the stop-frame animation from the original Terminator made in 1984 with the computer-generated Terminator in Terminator 2 to see how much of a revolution there was at the time. It's hard to believe that these movies were only made 7 years apart.
Get out.
Apart from general improvements from Moore's Law, both the Abyss and Terminator 2 were made with silicon graphics machines. They contained a number of these custom VLSI chips called the geometry engine, and this significantly sped up the geometry processing required for 3D graphics. Interestingly, about the top third of the chip is the microcode. Quoting from Jim Clark's 1980 Lambda paper, the geometry engine is a quasi-general purpose 4-component vector function unit. It gets its power as a result of its architectural simplicity. Almost all of its complexity is in the microcode that drives it. Writing the microcode and making minor additions to the principal bit slice to accommodate the requirements of the microcode has taken approximately 50% of the total design time. This was the point I was trying to make, and it's the reason I've documented this series on making the microcode for the SAP6502. Before we get into it, I want to go over some nomenclature. I use the term assert often, which really means active or on. However, this doesn't necessarily equate to a high or 5 volts on a wire. Similarly, deassert means inactive or off, but this doesn't necessarily mean logical low or 0 volts on a wire. The appropriate logical levels actually depend on the nature of the signal. If it's active high, then assert means high and deassert means low. But for an active low signal with a bar over it, assert means low and deassert means high. The control word uses both active high and active low signals, so I tend to use the words assert and deassert to describe what's happening. For example, if carry 1's asserted, it means the signal's high. But if update C with a bar over it is asserted, it means the signal's low. Unfortunately, this is just something you've got to get used to in digital logic. In the last video, we started working on SAP6502 cycles and Emulate 6502, which are the basis for the emulator. Now I'm going to start work on set micro instruction. You might be wondering why I have 2 function calls that are overloaded. Let's have a quick look at the layout for the memory in the microcode. You can think of this as being a 2-dimensional array, where the x-axis is the instruction and the y-axis is the step count. Step 0 is the fetch microcode, which is the same for all instructions. Step 24 through 31 is the reset microcode, and again this is the same for all instructions. The microcode between steps 1 and 23, however, is unique for each instruction, and not all instructions need to use all of these steps. In fact, none of them do. There's a microcode count reset signal, and this effectively ends the current micro instruction. Each entry in our table is actually a 40-bit wide control word. Hopefully we're getting pretty familiar with this by now. One of the things we want to be able to do with our microcode though is read the status register. If you'll remember, I use this 74HC151 8-to-1 multiplexer to multiplex all of the flags down to a single signal. This then feeds into a single address line on the microcode EEPROM. I've somewhat arbitrarily chosen A16 for this task, which means we really have two microcode EEPROMs, one for when flag in is clear and the other for when flag in is set. All of the other address lines are set to 0. I need a set microinstruction call function, which inputs the control word for a given flag setting. This lets me set a control word for one flag setting but not the other, while the other overloaded set microinstruction function doesn't take the flag, and in this case, it sets the same control word in both copies of the microcode. Let me start coding that up. Now you might have noticed that these function calls don't take the step number to program. Instead, I use g_maxstep, which keeps track of how many steps have already been encoded for a given instruction. I write the same control word for flag clear and flag set, and then I increment the step counter for that instruction. Now this time, I want to incorporate the flag bit. I pass it as a variable, then I use it to determine which of the two copies of the microcode I update. It should be noted that I only update the step counter when flag equals 1. This means when using a flag bit, I need to write the microcode for flag equals 0 and then write the microcode for flag equals 1. Hopefully I can remember to do this. It's not ideal, but it does save another function call. Excellent. Now I can actually start generating microcode. Program control ROM is responsible for generating all the microcode, and I only want it to be executed once. First, I want to clear the entire table of microcode to 0. Now I want to write the reset code for each instruction. Because this is the same, I can just use a simple for loop. Within the for loop, I call setMicroInstruction with the iRegLoad, PCClockLow, PCClockHigh, memAccess, and PCSelect attributes asserted. A bit later in the debug, I also added this driver equals high Z. It's not really used in this early version of the code, but it is used later. What does this look like on our control word? Well, it means all of these signals are asserted, but within our microcode, we make everything active high. This is how Ben Eder did it, and it's actually the easiest way to think about the microcode. But the signals themselves, we may want to be active low. Now, Ben Eder just used this large bank of inverters to convert all the active high signals to active low. In the SAP6502, most of the output signals are active low. I store them internally as active high, and the emulator treats them as being active high because that's the easiest way to think about them. I invert them in software before I write them out to the EEPROM. Much easier for me, but it might confuse you a little. Anyway, back to our fetch micro instruction. We know that these signals will be asserted. The first one I want to look at is PCSelect. This will select the upper pathway here, which means the program counter is driving the address lines. memAccess is asserted, but mWrite is not asserted. These two signals are connected up to the static RAM, and they'll cause a static RAM read at the address pointed to by the program counter. They're also connected to this 74HC245 bus interface chip, which will cause the output of the static RAM to be broadcast on the W bus. iRegLoad is also asserted, which means the contents of the W bus is latched into the instruction register. This in turn is presented to the microcode EEPROM. At the same time, we don't want anything else driving the W bus, so the source register is set to be high impedance. Remember that high Z maps to this unused output. This prevents any of the other registers writing to the W bus. After we've read the instruction, we want to increment the program counter by 1. To do this, we assert PCClockHigh and PCClockLow. To understand how these signals work, we need to go back to the 74HC161 up counter. To make a 16-bit counter out of these chips, we connect the terminal count output from one chip to the count enable input on the next. But that's not the whole story. A positive edge on clock on this chip can cause both a count and a parallel load. It uses the parallel enable input to differentiate between a count and a load. If this PE bar signal is low, then the load occurs, and we want to use this for jumps and branches. But if this signal is high, then we get an up count on the positive edge of clock, which is what we want in this case. PC clock low is hooked up to the clock signals on the lower byte of the program counter, while PC clock high is hooked up to the clock on the upper byte. Now sometimes when I make these videos, I realize I could have chosen better names for some of these signals. For the lower byte, I've called the load signal PCL-CLK, while for the upper byte, I've called it PCH-CLK. In retrospect, I probably should have called the upper one PCL load and the lower one PCH load. But unfortunately I didn't, so we're just going to have to live with the existing labels. These two signals, PCL-CLK and PCH-CLK, both come from the register decoding logic within the sequencer controller. In the fetch microcode, iReg load is driven directly from the control word, and I did this so I can easily change it from active high to active low if I want. I haven't specified a register for the decode logic to use. Output 0 will be chosen by default. This means that the PCL-CLK and PCH-CLK signals will both be high, or deasserted. This is exactly what we want in this case, and it'll cause the program counter to be incremented by 1. We'll see how parallel load works in a later video. So in summary for microstep 0, we select the program counter, we do a main memory read, we transfer this data from the memory into the instruction register, then finally we increment the program counter after we've done the read. Actually, let me expand upon that final point. During step 0, memory access goes low but memory write stays high, and PC select goes low as well. This means we do a main memory read from the address in the program counter. At the same time, PC clock high and PC clock low both go low, while PCH-CLK and PCL-CLK from the decoder both remain high. This means that the actual increment occurs at the end of the instruction on the positive edge of the upper two signals. This means PC clock high and PC clock low should both be high in step 1. If it's not clear in your head how this microcode instruction works, it may be worth going over it a few times. Once you understand this, the rest is pretty straightforward. We've chosen the TXS or transfer X to the stack pointer instruction to be the first one to implement. That's because it's relatively straightforward and it doesn't involve the flags. The execute portion of each instruction has its own function call, in this case, execute TXS. This micro instruction is a little more straightforward. We want the X register to drive its value onto the W bus. Conversely, we want to load the value into the SP reg. This means W bus source is set to the X register, and as a result, the XReg OE signal is asserted. W bus destination is set to SP reg, and as a result, the SP reg clock signal is asserted. Both of these registers have both their input and outputs connected to the W bus. Schematically, it looks like this. The microinstruction code asserts the XReg OE and the SP reg clock signals. The data transfer actually occurs at the end of the microinstruction when the SP reg signal is deasserted. This is just to make sure you're still awake, and to remind you how good the animation is in Terminator 2 thanks to the microcode in the geometry engine. At this stage, the fetch microcode lacks the high Z directive for the source register, but I will add that later. Now I want to add the microcode for the TXS instruction. I use a for loop for all instructions. Then this switch statement will have a case clause for each possible opcode. For 9a, I want to execute program TXS. I will relabel this execute TXS later, but for now I've just called it program TXS. This function call is pretty straightforward. It just contains one microcode instruction. Here we assert the output enable of xreg and assert the clock signal on the SP-reg. It also asserts this UC counter reset signal, which is another output from the control word, which signifies the end of the instruction and resets the microcode counter. Although I actually have 23 slots for microcode instructions for TXS, I'm only using one, so it's a bit wasteful. I need to connect program control ROM into the AppleWin infrastructure. There, that's done. Now I want to modify this emulate SAP6502 code to use the microcode. Upon entry to the function call, I want to copy the value that AppleWin uses for the registers into my own data structure. So that's the accumulator, index X, index Y, program counter, status register, and finally, the stack pointer. When I exit this function, I want to do the reverse. I copy all the values in G_SAP registers back to the variables that AppleWin uses. So far, so good. Next, I add this do while loop to step through the microcode for a single instruction. The step variable here is just a microcode step. It starts out at 0, and when it gets back to 0, I end the instruction. I need extra variables to represent the value on the address bus, the W bus, and the control word output. I'm going to use the fetch microcode for instruction 0, but it shouldn't really matter, I could choose any instruction. I need to model the address bus which goes into the main memory, and remember that this is under the control of the PC cell bar signal. When it's low or asserted, then the program counter is selected, but when it's high or deasserted, then the effective address registers are selected. I check to see whether PC select is asserted. Now, in the model it's an active high signal, but remember the signal going out to the real hardware is active low. If it is asserted, then I load the value of the PC register onto the address bus. Otherwise, I use the effective A registers. Next, I check to see whether there's a main memory read occurring. Mem access will be asserted, and mem write will be deasserted. If so, then I load the W bus with the value from main memory. This read macro is actually defined by AppleWin, and it'll handle main memory reads and all the memory mapped I/O that we need. If we're not doing a main memory read, then we need to transfer the contents of one of the registers onto the W bus. Now that we have an active signal on the W bus, we need to write it somewhere. If the iReg load signal is asserted, then we load it into the instruction register. If mem access and write are both asserted, then we want to do a main memory write. Otherwise, we want to transfer the W bus into one of our registers. We'll come back in a minute and write the read register and write register function calls. But for now, if PC clock low and PC clock high are both asserted, then we know we want to increment the program counter. Now, technically, we should be testing for an edge on these signals, but I'm going to simplify the model by only looking for a level. I can add an edge test later. Next, we want to increment the microcode step counter. If the microcode reset signal is asserted, then we go ahead and reset the step counter. Control address is the location of the next micro instruction, and we load that micro instruction into control wires. I went over that pretty quickly, so let's just recap. We set the value on the address bus. We read a value into the W bus, either from main memory or from one of the registers. We then write the value on the W bus into the instruction register, the main memory, or one of the other registers. We increment the program counter if appropriate. Step to the next micro instruction and load it into the control wires. Once we've finished the instruction, we exit the do while loop. Writing a value into a register is pretty straightforward. We have this function call which takes the register and the W bus value, and it just copies it across. Read register is a bit more complicated because we need to take into account the ALU. Now, from the machine's perspective, the ALU is just register 0. I'll implement this a bit later, but I'll just leave aside a placeholder. If we're interested in one of the other registers, then we just return the value there. Alright, I just need to clean up the code a little. Let's see if it runs. Excellent. Pac-Man's using the TXS instruction that we've implemented with Microcode. At the moment, it feels a bit like we've got a Christmas tree with one decoration, but the important bit is actually the tree, at least for now anyway. In the next video, I'm going to start working on addressing modes, so don't forget to like, share and subscribe.